a project I'm working on, so I think
Yeah.
we visit for AFRL doing some oxidation testing,
Okay.
and then resubmitting the paper for reviewing the results. For the resubmission is due at the end of this month. So.
Oh. Well, anyway, this other meetings. Yeah, that's too pricey for grad students. I don't know why. The polymer ones, like this SPE we were just looking at, and it's like it's $50, and the rubber division, like ACS, is $50. And if you present a talk, it's free. So it's like if you don't present a talk, but if you present a talk, it's free. So for both of them, I think. But I think they give like 1 day free if you present a talk, but I don't know. So the 150 is out of line. It's not normal. Let's see. This will give me a new version of this thing. Anyway, so see, I guess it might be just you two guys here today, but yeah, I think, did I say record on this thing? Yeah, it's recording. The audio. Hopefully. Okay. Thing up. Just slow. All right, it's okay. Anyway, so anyway, I didn't finish grading the homeworks, but the ones I did looked okay. Like I think they were pretty good shape. And then so next section is the surfaces business. So I want to get started on that. So anyway, so the issue is like when things get smaller, like this is an enthalpy of formation for salt. So if you grind salt down, this energy formation goes through the roof. Right. So it takes energy to make surfaces. That's why that happens. So this is per like mole. So basically a molar, this thing has an additional component. It's like the surface energy that adds to the bulk. So this is per mole, so it's per volume kind of. The volumetric enthalpy and then the surface enthalpy. So you end up, when you write that out, there ends up being like a kind of a magic size falls out of that. In other words, if you have bulk enthalpy, bulk entropy, bulk gives free energy, then this term, if you divide by the volume, you end up with a size. So you end up with a magic size if you set the free energy to 0. So that kind of introduces like a critical size related to the enthalpy of the thing. So anyway, so that's kind of the behavior partly. There's a paper here. Let's see, surfaces, this grinding thing. It's kind of a simple paper, but I guess it's from 2009 from Germany. But all they did was grind things and then measure and just measure well, the energy it takes to grind something gets higher. So that's why, like when you like the beach sand doesn't eventually just become like nanoparticles, because the energy, like to make more and more surface area, the energy goes through the roof, right? As the particle size gets smaller. So basically, then in this paper, they found out that there's something happens, like there's a true limit of grinding, like where you can, maximum that you could possibly grind it. So this plateaus out. But there's this apparent limit. And the apparent limit is because the things aggregate together. So once you get so small, then the surfaces want to cover each other up, and then they reform kind of clusters. So basically in grinding things, you can only go so far, and they can't even go as far as you could possibly go because the things will cluster together. So you end up with about half the size that you could get if you ground it, if you could actually get the surface size that you wanted. So yeah, in diffraction, you can see the peaks broaden when you get smaller particles. It's like when you have large grains, then you have these spikes, and then when they get to be nanoparticles, you get a broad peak, and the half width at half height, 1 over that is related to the size of the grain of the crystal. That's called the Shearer equation in diffraction. So if you look at polymer, like if you look at metal crystals, so if you have a polymer which has nanocrystals, and then you put in like a filler which has kind of macroscopic grains, and you do a diffraction pattern, you can immediately tell the filler because it's got these spikes, and the polymer itself is these broad peaks because it never forms large crystals because of defects and because the chain has a finite length and a few other things. Kinetics is slow. Anyway, so he's just showing like, so that partly the size that you can get to by grinding has to do with the modulus, and partly it has to do with this idea that the surface energy form makes it want to agglomerate further. Right? So you can't actually reach the limit that you could get to. Anyway, that's an aside. But so, hey, let's see. So if you have a liquid or gas interface, some kind of dense phase and a gas, it's called this surface energy, surface tension. And then if it's a liquid, solid liquid, you call it an interfacial or interfacial energy. So it's interface versus surface, and all the equations and everything are the same kind of for those two things. They aren't exactly different. It's just that we see them as different because the surface you think of with air usually, right? So anyway, if you have two phases and then there's an interface, you can think of it as having a width, or you can think of it having like no width. So it could be a discrete step, or it could be this kind of gradient thing. So usually the gradient thing, like having an interfacial thickness, is kind of what people think about, right? And that's due to Gibbs, I guess, Gibbs interface. All this stuff is basically Gibbs. Like Gibbs came up with the idea, like you could have the free energy. Well, he invented free energy, and then he came up with the idea that you could add in terms to it. Like you just add in a term about the surface, or you could add in term about the electrical potential or the magnetic field. You can just keep adding whatever terms you want into a free energy expression, right? So if you're adding in a surface, you have this term that gives you this. Basically, this is the Gibbs-Thompson thing, that the energy to form is going to raise up as the particle size gets smaller. Right? So anyway, so Gibbs is the Mr. Surface. He's like 1880s in Yale. He was like the first PhD, I guess, in the US for engineering. So he's got some claims to fame. And there's a number of equations and terms that are named after him, but I think they didn't have the Nobel Prize at the time when he was around. Anyway, so you talk about that region. So you could think about, so you have two components like A and B. The components can be depleted from that region of the interface, or they can be enhanced. So you can have this kind of surface excess of the components. And then you can also have excess of all the different thermodynamic properties. Right. So basically like the internal energy can have a surface excess. Right. And this is called adsorption of the component at the interface. So this absorption and adsorption. So adsorption is this interfacial thing, and absorption is like kind of like a sponge. like if the body consumes something, then it, like a sponge takes up water, that's absorption. And adsorption is going to the surface of the thing. It's just like one letter difference, but it's easy to swap out those words. So we're talking about adsorption for everything, like gas absorption to measure the surface area of particles, for instance. Right. So, and people will call it absorption, but it's not right. So probably doesn't matter. But anyway, so that's the adsorbed molecules at the interface. That thing. This is basically from the book, you know. So anyway, so the change in, yeah, so you can talk about the change in internal energy at the surface. So it'd have, so du's PDV TDS, so minus PDV. And then if you ignore volume change, then you get this equation. You add in the chemical potential, the components that are going to the interface is DNI. And then you can write basically an expression for the surface excess internal energy, right? So if you then, so in addition to that, so this is just considering it without considering the this excess energy that has to do with the surface tension, like the surface force, the energy that it takes to create a surface, right? This is kind of just the bulk. So just having an interface ends up giving you a change in the entropy, and there's a change in chemical potential to locate things at the interface, right? This excess energy to locate things at the interface, and that entropically there's going to be a change. Additionally, like creating an interface takes an energy. So that's what this surface term is, like the surface tension. So you have like these bulk properties. So it'll change because you put things at the interface. So definitely the entropy changes because you have to locate, or if you have atoms floating around here freely in A, they have a lot of entropy. If you say they have to park at the interface, they have less entropy. So that's a direct change in their kind of randomness, right? It's almost like crystallizing. They have to be right at that spot, at least in 2D. They have to be on a 2D plane. So there's definitely a change in entropy, and there's a change in the chemical potential because the environment of the atom up here is different than the environment at the interface where it has to interact with beta and alpha phases, right? So, but in addition to that, just creating the interface has this energy, right? So typically this idea of like a surface energy. So this would be like, since none of these terms have area, this has area. So you say the change in the internal energy with respect to area is this surface tension or interfacial energy, right? So the way that was kind of thought of originally, let's see, this is slide 7, is like, so there's different ways to kind of look at it. So this is like if you have a film, right? So it's an interfacial film between gas and liquid. And so the film's here and there's no film over here. So you pull this down, right? Then you create this interface, right? So in pulling it down, you put a force on this wire. So like a bubble, right? So you put a force on that wire and on that wire. So you have two L's. So depending on the length of that, the force increases. So the force that it takes to pull that down divided by 2L is definition of this interfacial energy, this gamma or sigma. Gamma would be for interface and sigma for surface. Right. So this is kind of one way to look at it. Like you're creating an interface here by pulling this thing down, then that interface. Anyway, so it's going to be basically that's the idea. Like it takes energy to create that interface, and that idea came from the idea that this kind of film thing. Like when you make more film, it takes energy to make it. So that's kind of the idea of this thing. Anyway, so then kind of from that you can get the Laplace equation, right? So you have so the Laplace equation is that the pressure is related to this surface energy divided by R. Okay, so that functional form should be kind of, so this is like force per area. This is energy per area. And energy is force times distance. So this is force times length, force divided by length. Just like just like I showed, when you have that soap film thing and you pull it down, it's a force per the length of that bar that you're pulling it down with. And there's two bars, one at the top and one at the bottom. So it's 2 times that length is related to the force that you pull. So the force divided by the length is the surface energy, which is also the energy divided by area, because energy is force times distance. It's force times distance divided by force times distance gives energy, and if you divide by area, that gives surface tension. Or you could call it force by length. See, the force by length or energy per area, right? It's kind of like two ways to look at it. And it ends up being the same thing, right? So if you look at this equation, it's like force per area, so it's going to be energy per length, because energy's force times distance. So anyway, that works out unit-wise. So that's called the Laplace equation. This thing has kind of a strange behavior. It says that say you have a droplet of water, right? So if you have a droplet of water, and then you're at 1 atmosphere, so 0.1 megapascal, and then you're at macro, so 1,000, this is like a centimeter, I guess, or millimeter droplet of water. And then you take that and you reduce it by 1,000 times to a micron. So you'd think like, I mean, you wouldn't think much about what the pressure would be inside a micron-sized droplet, right? But it turns out it's 100 megapascal. It's 1,000 atmospheres. So it's like a huge pressure inside a little droplet of water, like rain droplets, which means like, so a lot of things happen at high pressure. Like you can have phase changes. You can have like chemical reactions go nuts. When you put high pressure in a chemical reaction, the reactions just go crazy. Especially if you're producing, depends on if you're making a higher or lower density material from the reaction, right? But if you're making a lower density material, you can drive the reaction to be like basically thousands of times faster just by putting something into a small. So something like this is partly why like grain elevators blow up type thing. You make fine dust of the grain, and then all of a sudden, like the pressure inside those things allows the reactions to go like crazy. Plus the surface area is much higher too. But anyway, so this kind of thing could be taken advantage of. And it in the environment, like when you have rain and you have sulfuric acid from the coal plants, and then like this kind of pressure inside the raindrops is going to make it a lot of the conversions and reactions and things happen a lot faster. Right. So anyway, so that's how this Laplace equation, it might seem kind of trivial, but basically it's kind of an important thing to think about. Also, it ends up being a basis for the Gibbs equation for how the free energy forming nanoparticles and things. Anyway, so we have that business, and then so you can get that equation by doing that free energy, retain the pressure volume terms, and then include the surface terms, and then say that the volume. So if you have this dl for the interface, the area times the dl is the volume, and then you have the pressure is this dl times the force, right? Let's see. So we have the change of volume would be dl, and then the d area is going to be there's also going to be ASDL, but divided by this curvature term. So the area, so if the curvature is going to be 1 over r, so to get the area, you have the thickness of the interface, and then this other term that has to do with the curvature of it. So if it has no curvature, the change in area is 0 as you do a change in length of this gap. But if there's curvature, then so curvature is going to be 1 over r when 1 over r, when r is infinity. In other words, r would be the radius of a sphere that would touch the interface. So you have an interface that's wavy, you try to park a sphere next to it and it has a radius that matches the curvature at that point. But it could have different curvatures in the X and Y direction in this interface. So you can have two types of curvature, C1, C2. And that's what gives rise to this kind of area-based energy, like the curvatures putting tension on that line. So that's going to be an energy term that comes in. So basically, the area, the DAS is going to be the curvatures, the sum of the curvatures. Is going to be, if it's a sphere, it's going to be 2 times R times AS times DL to get the DAS. And if it's a flat surface, these two numbers are 0 because 1 over infinity is 0. It would be an infinite diameter sphere to match up with the surface. Anyway, so you can substitute in, get the same ASDL, and then have the pressure difference. So PdV is ASDL, and then the surface difference DAS is ASDL, and then you end up with this thing. If you set du to 0, then this thing equals that thing, and then you have this Laplace equation that the pressure difference inside a droplet is going to be the surface tension times these two curvatures, which if it's a sphere, it's 2 times sigma by r. It would be like that equation basically with a 2 in front of it. All right, so all right, so you have, like, if you have a crystal, so the facets of a crystal have different energies, partly because, in other words, if you have 1, 1, 1, the 6 nearest neighbors on that plane, that means there's 3 bonds across it. It's basically the bond energy from the interface is what governs the energy of the surface. Right, the 110 has 12 atoms in it. You guys know these Miller indice things, right? Does everyone know that, or like what 111 means? Do you know that? Okay, good. Anyway, so that's how many nearest neighbors, and that decides number of bonds. So the homework this week is see if I can get out of this guy. Is this thing. So he's crystallizing calcium carbonate. So I was at Sheffield. I was in the chemical engineering department. These guys were right down the hall, but I never met these people. Anyway, they've just published this year, and it's about calcium carbonate, which is like limestone, basically. So, and it's also like stalagmites and things that form in caves, stalactites and stalagmites. Right. So calcium carbonate is kind of a all over the place kind of chemical, but it usually forms in water, though, like in an aqueous phase. So it precipitates out of water, and it's got a fairly complicated structure, and it's got a huge number of polymorphs. So there's multiple crystal forms it can make. So he's talking about how, so when things crystallize out of solution, a lot of things happen, right? So he's talking about, so basically you need a supersaturated solution. So you have to get the concentration above the equilibrium for the crystal in order for the thing to start forming. And once you go to that above concentration, so supersaturation condition, you end up with something like this. This is a simulation. So he's got this supersaturated calcium carbonate, which he calls amorphous calcium carbonate, AAC. I forget what the other A is for. Oh, ACC, amorphous something. Amorphous is calcium carbonate, and H means hydrated. So it's got this water molecules kind of attached to the calcium carbonate molecules. In other words, it isn't exactly in solution, they're ions. So it makes a calcium ion and a carbonate ion, or it can have a hydrated carbonate also. And then anyway, it forms this concentrated solution, and then there's a crystal below, right? So it has to basically kind of forms that situation before it forms a crystal. So he's doing a simulation where he changes the mole fraction of calcium carbonate in the solution in a simulation and measures this interfacial energy between the crystal and this concentrated solution. So somehow the interfacial energy goes up, right? So the point is, like, when you have a crystal and then there's bonds, there's like loose bonds up here. In other words, the things are missing, like something's missing from the crystal. You're happy, A, B, A, B, A, B, and then you get to A and there's no B, right? So you have like a loose bond that has to do something. So he says in the simulation, he has water in it. So one of these is water. A is water, like the area coverage of water. O is area, I think. O is like area in a lot of these papers. So anyway, so the density of water in the z direction from the surface of the crystal. So as he increases the concentration of calcium carbonate, so the water is covering those bonds, those loose bonds. So those loose bonds have a lot of energy. That's the surface energy. That's why the surface energy is high, to begin with. So the water covers those bonds, and then that reduces the surface energy. But as you add the calcium carbonate and make the concentration higher in that interfacial layer, the calcium carbonate shows up at this 3, and it like reduces the water that's protecting these loose bonds. So you end up with more loose bonds, and that kind of makes this energy go up. That's basically the theme of this paper, So it's a short paper, only like 3 pages, but so anyway, so that's I think that's kind of the same idea of what I was trying to say here about this idea that you have the bonding scheme. I guess we're somewhere here. But you're going to have like the number of bonds besides basically the energy of the surface. I mean, partly it's proportional to it, right? So and then it's like the bond strength would impact. So the higher bond strength would give you higher surface tension. Higher modulus is really the higher bond strength. The higher modulus materials have higher surface tension. Right. So it's kind of like everything is kind of linked together. So surface tension isn't like a mysterious thing. Anyway, if you take like a cubic crystal, right, and you have 4 sides. So the A is the area of the side, and H is the radius of the cube, kind of like half the diameter, half the length of a side. So you take the area times the side would give you kind of the volume. You'd need to multiply by 2. If you sum up the 6 sides of the crystal and divide by 3, then you end up with 2 times the radius times the area gives you the volume. So it works for a cube to do that. You see what I'm saying? The 6 sides on a cube. 6 divided by 3 is 2. 2 times the radius times the area gives you the volume. All right. So hopefully that works. So this rule like works for any shaped crystal, like octahedral, whatever. Turns out that works as long as you take from the center out to the surface, you can get the volume of the crystal from that. Right. So that's kind of useful to do this Wolf analysis of these things. There's a paper, I think like the past couple of years I gave a paper on this Wolf construction, but I didn't do it this year for some reason. But anyway, the surface excess free energy is the surface interfacial energy. It's called surface energy here, but interfacial energy times O is the area again. Like they use O for area for some reason. There's probably a reason. I don't know why, but they use O for area. A must mean Helmholtz free energy, and then they don't want to use that maybe. But anyway, so draw factor center, and then you get this thing that we had that let's see. H is this is surface energy times the constant is proportional to the height. That's the Wolf construction. So distance from center to an interface of a crystal to the facet of the crystal is going to be proportional to some number times. So the distance for a large surface area energy, this distance gets larger, which means that if you think about it, the distance to the other surface has to get shorter, which means the area of the other surface has to get larger. So the area of the high energy surface gets smaller by this rule. That's how you do the Wolf construction. Like if you want to figure out the relative surface energies of all the faces of a crystal, you just measure from the center, the radial distance from the center, and that gives you the ratios of all the surface energies for the different facets of the crystal. If you have single crystals, right? So anyway, so this is a popular item. Like in the, let's see if every time I hit escape, it's not in this, it's in the other thing. So this guy shows up again. Like if you look, like last year's homework 7 is this Wolf shapes of crystals. It's a paper from 2021 where they kind of go through that whole thing, and they talk about they're simulating crystals, crystal shapes, and using that Wolf construction to kind of do that. And you can glance at that if you want. But anyway, so people are doing that. People use that kind of routinely to talk about the shapes of crystals. Doing this what's called a Wolf construction. So anyway, this comes from this business combination of this thing and the idea that, and this thing that you have the volume is this thing is just a geometric fact, right? And this is just a thermodynamic definition. And if you combine those two, you can get this Wolf construction equation. That's the idea. So to take let's see, so how do you do that? The change in volume, you say, is 0. So the derivative of this distance to the center times the area, you say, is 0. The derivative of that times 1/3. So your volume change is 0. So you just have to rewrite this thing in terms of the volume change. Or wait, the Gibbs is also 0. Like the sum of the Gibbs, if you're at equilibrium, is 0. So you're at equilibrium, the Gibbs is 0. Derivative of this thing 0, derivative of that thing 0. Right. So then that means the sum of the two is 0, and then that means that the height minus gamma minus some constant times the surface energy also has to be 0. That means that this argument has to be 0. This argument kind of fails for me because both the del, well, anyway, I guess it works because this is how it's done. Basically, you take that this Gibbs thing has to be 0, and this thing has to be 0. That means the sum of the two has to be 0. And then you can equate the arguments in there so that these two things have to equal each other. I mean, this equals this lambda times gamma, which is the Wolf construction thing. So hopefully that kind of makes sense. But anyway, the point is that remember this equation, that the distance from the center to the face gives you kind of the surface tension, which it's almost like obvious that would be true. I mean, if it's harder, if it's a higher energy, you want to minimize the area. That means the distance would have to get greater if you have a 3-dimensional object because the other surfaces grow. Like say you have a cube and the 100 faces have the highest energy, then you would want to grow a rod, right? You just want to keep growing up because the 200 and the 300 would have lower energy, so they could just grow at will. And then the 100 would have to just kind of not grow. So you'd end up with a rod. And if you had just one, like the 100 was the lowest, and you'd grow a sheet. Because the two sides, you'd want to minimize the two sides, and the 100 doesn't matter, so you just grow a sheet structure. Right. This kind of all right, this is one way to look at it, but the problem is like there's crystals that have a high surface energy for like a sheet structure crystal that have highest surface energy for the sheet side that form for other reasons than just energy balance like this. Polymer crystals example, because a polymer will crystallize by chain folding. So you have a long chain and it has to kind of fold and knit itself to form a crystal, and it forms a sheet crystal when it does that. But it does that not exactly for this reason. Like I'll go through why it forms crystals like that, but there's a lot in crystal shape that's pretty interesting to look at if you're interested in that kind of geology kind of mindset of things. But anyway, Let's see, let me hide this guy again. So let's see, losing track of time here. So anyway, so this is that this is basically the Laplace equation, right? So 2 times surface tension over H gives you the pressure difference. And then what is this saying? Pressure difference for solid crystal facets. I think this is taking this this equation, the Wolf construction. The Wolf construction is that gamma over H is lambda. Where does P come? Oh, P comes from the G. I don't remember how this fits together. This is part of this thing. Anyway, that's just the Laplace equation. The two things are related. I think that's the point. The Wolf construction and Laplace are related. I don't see the connection right now. I'll have to get back to this, I guess. Oh, I guess it's something like if you substitute for area here, I think that's kind of what's going on. Actually, it's not really clear what this slide is for, but it's here. Anyway, so then in the book, he goes through the periodic table. So I thought I'd mention like groups. So it's set up into groups and periods, right? So you have like group 1, 2, 3, 4 to 18. And these don't have surfaces because they're gases, right? So you only have 16 kind of groups to look at. And then there's these periods, 1, 2, 3, 4, 5, 6, 7, right? So these are also broken down into the D block is like the transition metals in here. So these things can have different ionization states, like iron, right? Nickel. And then the P block is like over here, the semiconductors, and then the S block is like this side. Right? And the F block is this stuff down here, the weird things. Right. So he's talking about mostly D block in this book. He concentrates on transition metals. So this is basically he's looking at periodic trends, surface tensions, like liquid elements. So the D block is 3 to 12, right? So it's kind of like the 3 to 12 groups, right? So these are the groups up to 16 because at 18 are gases, and then hi. So basically, there's a peak in this, right? In the transition metal region, like 4 to 12, whatever. There's a peak. That's because the D block transition metals have strong bonds. So basically, the bond strength couples with the surface tension. That's the point of this, right? So, and then the surface tension versus the anything that has to do with kind of cohesive energy density of the thing, like the vaporization enthalpy. So they kind of linear in that. So it's anything that has, you can kind of predict this is against the melting point. So the higher melting point has more cohesive energy. So the surface tension goes up with melting point. So it's kind of basically, he just shows some trends in the book about basically that the surface energy or interfacial energy has to do with the cohesive energy of the material, like the modulus, the melting point, the heat of vaporization point, heat of vaporization. Everything's kind of linear in that. Then this thing, he gives this empirical equation. But the reason they went to this equation, so it's a liquid, and then this is a liquid, and Tc is the like would be the melting point, right? So he gives this equation, and he says N is 1.2 for surface tension. But the reason he gives this I mean, they picked this form is because of the thing like delta G is delta H minus T delta S, and T delta S is delta H over T star. So you set delta G to 0 and you get delta S is delta H over minus delta H over T star. So you end up with this kind of form, and that's the same form. Right. So this is like a natural form for an energy. So you'd kind of just use that and then see if it fits, and then find that it's got a scaling parameter here to correct for the problem. So this is across different materials for the using like the melting, or this is like maybe the boiling point. Could be melting or boiling point. Sigma, so it's the surface to the gas. So that's the vaporization temperature, equilibrium vaporization, and how it changes with how the surface energy changes with temperature, right? Just according to this kind of Gibbs function. Right, so he gives that. All right, so this is from a different book. So there's a bunch of books on the web page on surfaces. So everyone, like, there's different approaches to surfaces. I mean, like metallurgy has an approach, which our book kind of gives. You know, it's actually a little confusing, the metallurgy approach. The chemistry approach, so this Adamson physical chemistry. So if you want to look at these things, you have to put an F at the end here. Like, this is like a classic textbook for chemists, you know, for kind of in the surface film, whatever, blah, blah, blah. So if you want to, this is like the Bible of physical chemistry. And then Heimitz has a good book on surfaces. Same thing, put an F at the end. Istrailovich is an Israeli guy who has an Israeli name, I guess. But anyway, he's a pretty famous character. I think like runner-up for Nobel laureate or something. But anyway, actually, he was in Israel, and now I think he's in California. I think he's at like Caltech or something. But let me fix this thing. So anyway, so this is like the Bible of soft matter surfaces, like gels and polymers and things. And then DeGennes won the Nobel Prize. He wrote a book on surfaces. That's kind of worth mentioning. And this is our book. And then I taught a course a long time ago about nanoparticles. That's that course. And then, so you might want to flip through those things if you're interested. Then at the end, I want to talk about block copolymers, which are surface dominated. So there's a few things on that. Surface science, surfactant science is about surfactants, which is organic molecules to modify surfaces. And then there's some other book here. I guess that's it. So anyway, there's a few books on surfaces. Our book, and there's a few books that might supplement, you know, so I mishmash that into these notes a little bit, because our book doesn't really cover the contact angle and gas absorption measurements, which are like common techniques to use to look at surfaces. So I thought I'd put those in to kind of mention what's going on. So I mentioned, like, if you want to, so instead of saying energy per surface, you can say force per length. And this kind of shows you where that comes from. Like if you have a bubble and you pull this down, it's going to take a force to pull this down. The length is two lengths, this side and that side, so that the force is going to be related to this kind of material property, which is a surface tension, and then times 2 times the length that you have. So that's basically kind of the Laplace equation, or less, for pressure for bubbles, in a sense. Then you can do this, what's this called? This is a Wilhelmy plate method, which I guess a German guy invented, probably. So you dip a plate into a liquid, you pull it up, then you're going to get a meniscus form along the side of it. So the force that you're pulling up on this thing has to match the force that the liquid is pulling back. If it reaches equilibrium, then the force pulling up, there's a tension you have to put upward, has to match the tension that the liquid's pulling downward with, right? And that's going to be a force in this kind of vertical direction. If you measure the angle at the edge of this thing, then that the sine would be this side and the cosine would be that side. So you end up with like cosine of that angle gives you the force it's opposing lifting the Wilhelmy plate out of the liquid. Right. And so there's various ways people have figured out how to measure the surface tension for gas liquid. Right. There's not one method. This is called the tilted plate method, where you have a force of tilting the plate. And when you reach equilibrium, the tilt of the plate where this thing's normal, like the liquid film becomes normal to the surface of that, you can get the contact angle from that. And again, it's going to be cosine of the angle is a force in the horizontal direction that's related to the force of tilting the plate. Right, so there's always going to be cosine of the angle involved in these things. This contact angle, the contact between the liquid and the solid. So if you do the force, so if you have also if you take a capillary like a straw and you put it into a liquid, but you get a meniscus here, but in the middle of it you get a meniscus of the liquid, and you can measure the angle of that. And again, like the force going up and down, the sine would be this side and the cosine is that side. So the force up and down is cosine of the angle times the force would be this is force per distance times the distance, which is the radius of the circle, 2 pi to get the circumference of the straw that you're using. So that gives you the force that the liquid is pulling the fluid up with, right? And that's got to equal the mgh energy or force pulling the liquid down. So that will give you a definition of the capillary suction force on like a tree root or something. Like trees pull water from all the way underground all the way to the top of the tree. And this is the force that they use to do that. So they need to have capillary of the right diameter to get the right height of the tree. Right. So trees have small capillaries in the wood, right, that pulls the water up. I mean, there's no pump in a tree, right? So the water has to get up somehow. That's a Wilhelmy plate. It's the same kind of balance, and you end up with an equation to get this contact angle from it, or to get the surface tension from it, this gamma. Then this is usually in the lab. This is what you see now. Is like you put a drop of liquid on a solid, and then you take a photograph, and you can from the photograph you can either with a computer analyze it and get this contact angle. And this is going to be a force balance along the surface of this. So again, the contact angle, and then the sine would be this side, cosine's that side. So it gives you the force of the liquid on that side, and the force. Then there's a force of the solid air, and the air liquid, and the liquid surface. You want the contact angle of the surface and the liquid, so you can get that basically if you know the solid gas contact angle and the liquid gas surface tension, then you can get the surface tension that you want, like the solid liquid. Same kind of arguments for the force balance of that. So this is the Young equation. Dupree showed up later on, but maybe Dupree was earlier but ignored in the English speaking, whatever. So this kind of force balance thing and angles is kind of, so if you do let's see, do I have pictures of this? So there was a paper that we did for homework on this thing too. This is a big deal in metallurgy because you're going to have like grains, and then you can look in a micrograph and get these angles, and from that you can get the surface energies of different phases. Right, so that's kind of the idea. Let me see if I can find that thing here. There's a couple papers on that. I think it was in homework a long time ago, like Seafolf shapes. Let's see if there must be inside here. There's a paper on this kind of thing. I mean, this is like so common. You can anytime people are doing grain analysis of grains and micrographs. That's real crystallization from solution. no, that's a book. That's actually a book. Can find that. Circulation of gold nanoparticles. I don't see that. There's a couple papers in here somewhere, but I don't exactly see it. There's a lot on surfaces, like it covers so many different fields. Anyway, so this is pretty, there is a picture in the book on this thing, so just like here, right? So this is from some paper from a long time ago, but basically they did a micrograph and they figured out that this was, they etched this thing, so it came up, they can get this angle here and they can get kind of the interfacial tension, interfacial tension between the phases from the angle in this thing. But there are a bunch of papers on this. Like you can find a lot of papers on just getting the measuring these angles of that thing. So anyway, so this is basically a force balance around the angles of this. So the sigma times the tangent line, and the tangent line is going to be 1 over the sine of the angle. So you end up with the sigma divided by the sine of the angle. So the angle sigma alpha beta would be the angle chi, and sigma beta chi would be the angle alpha. So it's always the odd one out to get this. And that's the same as this rule of sines for triangles. It's kind of the rule of sines for triangles. But anyway, that's how you get the, like you can get at least the relative surface tensions between the different phases by optically measuring or by electron micrographically measuring the angles of the grains in a metal. Right. And then that will allow you to, I mean, it could allow you to verify the composition you think the grains are. Because if you know, I mean, you can look up these numbers for surface tension or interfacial tension between the phases. And then you say like, this is phase chi beta alpha. And you can, by that, you can verify it in the micrograph that what you're looking at is what you think you're looking at. Right. So that's like another tool. Like you can do EDEX to get the composition of the phases, and you can do electron diffraction to see like the crystallography of them. Then you can also verify it with these angles. Just all those things should agree. If they don't, then something's messed up. Like if they don't, that means there's something at the interface interfering with the interaction between the two phases. Or you could have another phase showing up at the interface. I mean, there's a lot of things it could be, but usually you want to verify composition, you know, from various angles if you're doing that kind of work. So that also has come up in a few other, even in polymers, people have that. There's some papers on block copolymers in here that use that same kind of approach. It's from a book, I think. This is from Wikipedia somewhere about how you can measure. It's basically the rule of sines again, I think. This is a Wikipedia page. I don't remember exactly what this is, but coexistence of 3 fluid phases with the angle. I think that ends up being the same as this sine, rule of sines, same as this thing, except just one of the angles is 0. So that ends up giving us this equation. And then he's showing the various things you can see in a micrographs of like metal phases, like what kind of design, you know, it's how this can end up appearing. So basically, to identify the phases by the surface energies, if you see this, then you know, basically you can apply this equation with these known surface energies, and you can kind of create these different structures that appear. I think that's the idea of that. This looks like the same thing we were looking at for the cathode material, right? It's got cobalt, iron, oxide. It's like a lithium ion cathode. All right, so then you get, so there's like 3 ways to talk about making nanoparticles, right? So this one is this Thomson's equation, which is basically this is just like the, so if you take the Laplace equation, so we had the pressure difference is 1 over the size, and you do a differential of both sides of that, then you can get that, you can get the pressure, let's see, you can get the deep pressure here, and then because the volume, the molar volume's here, that's also got a pressure on it, so you can get the d pressure over pressure is d of this Laplace term, this 2 times the surface energy over r. And then that thing would mean that you'd have like log of that pressure difference is the surface energy over r, which this ends up looking like the pressure that you have for a bubble or droplet, either one, is going to be equal to the pressure of an infinite size phase. It's not curved, right? And then exponential of the energy, which would be like the surface energy times the area, and then the r's cancel out, normalized by the RT. So basically this is kind of like a Boltzmann function. It's like energy over RT gives you the probability of something happening, which would be like the pressure. Pressure is the infinite pressure times this energy over RT. Right, so that's kind of the way you'd expect. So if you did that, you'd expect to take like, actually this is plotted wrong. It should be log of the pressure ratio versus 1 over r would give you a straight line. That's why it's not a straight line. So the way this equation suggests you would plot log of this thing versus 1 over this thing. They plotted it, this thing versus log of that thing. So hence it looks like that instead of a straight line. It would have been better to plot this differently. But anyway, so that's the behavior. As you go down, the pressure of the bubbles get larger, following this kind of exponential energy over RT. And they end up, from the analysis, you end up with a size from it. So if you want to get a big pressure, you end up with a small size. And it's an exponential dependence between the two. So that's kind of the signature of a Gibbs-Thompson equation. You have the exponential of the energy over RT is going to give you the thing that you want, and there's going to be a size that comes out of it. In other words, you've added in a free energy expression, you have a size that comes out, and then it gives you this other value, like the pressure, in this case, the pressure. So if you wanted, say you use it the other way, say you wanted to get a particle size that was small, right? Then you would have to go to a big pressure differential. Like in other words, if you wanted to get really small particles, you would have to have a huge pressure. So far from equilibrium. So this ratio is like how far are you from equilibrium? Log of how far you are from equilibrium gives you smaller sizes. The bigger that is, the smaller the size. That's kind of the Gibbs-Thompson thing. Go far from equilibrium to get small sizes. It's like, how would you make nanoparticles? Well, or where would you expect to see nanoparticles? It'd be like someplace where you have a huge pressure, like in a nuclear bomb explosion. I mean, you're going to get tons of nanoparticles flying out of that. All of them will be radioactive cesium. So basically, and that meaning nanoparticle in that sense, meaning that the dispersion would be huge, like they would just go everywhere, which is what happens, right? So basically, or if you want to manufacture nanoparticles, like making titania or silica, nanoparticles, you make a rocket engine. So really high pressure, high temperature, like an explosion, and then you can make, that's how paint is made, like titanium paint is made in a rocket engine, tied down to the ground. They just blast through TiCl4 and torch it. And it's just like kind of an explosion. And they make that kind of process used to make like train loads of stuff, like huge amounts. Like every paint that you have has this stuff in it. Paper, like white paper is made from that. Right. So anyway, there's a lot of industrial processes whereby kind of accidentally they figured out like to make things small, you have to go far from equilibrium. So that's like the main theme of there's 3 versions of this kind of Gibbs-Thompson equation. This is one of them. Is this like pressure differential and the particle size. what this is. This is absence of nuclei, initial bubbles when boiling can be very small. Right, this is bubbles. So there's a free energy expression. Oh, liquid and gas are in equilibrium. The liquid doesn't really have a volume, to ignore that term. And then well, the entropy difference of boiling, the volume of gas, and S is H over T. So you're going to end up with 1 over T squared from the, if you do the derivative. Oh no, you substitute for volume over for ideal gas, you end up with T squared, like in the Clausius-Clapeyron equation. And then you have dP, when you did ideal gas, you get over P. So you end up with log P, and then derivative of 1 over T for this thing. See, this is the same as the Clausius-Clapeyron equation, but you end up with this log temperature differential in the log of this pressure, surface energy pressure term. I think the end result is that you get log of the size, and you get this, the quench depth gives you smaller particles. That's the bottom line. Deeper quench depth gives smaller particles. So they're going temperature of vapor, oh, smaller, this is liquid, these are liquid gas bubbles in boiling. So this is a whole nother area of research interest for people, especially for nuclear reactors, because inside a nuclear reactor, it turns out our nuclear reactors are really hot. You know, like a small nuclear reactor is like a huge coal plant. So basically, there's an enormous amount of energy being dumped into water, and then it's being converted into steam, right? And it's all radioactive. So you basically make really small bubbles in that process. And that thing, so there's some papers, and so especially at Oak Ridge, there's a lot of people doing work on bubbles. Let's see, there's a couple papers in here. There's this whole group's just looking at nucleation of bubbles in water in nuclear reactors at Oak Ridge. There's like 20 PhDs doing that. Nucleation, nanobubbles in nuclear fuel. This is one thing. These guys are in China, but also interested in nuclear stuff. It's just about how these bubbles nucleate, because the small bubbles have this enormous amount of energy in them. And then that can lead to like degradation of the vessels and things. So basically the lifetime of the reactors are related to these gas bubbles. Like if you can somehow reduce the gas, you can see what it does to a metal. Like the bubbles show up and destroy the metal for the reactors. You know, so there's a paper on that in here. It's also a surface effect. So it's kind of like you can see like this stuff hits everyone is going to be using surface things. Hence why it's here, but it's also kind of like a disjointed a little bit topic. Anyway, so what is this? This is this bubble thing, right? Let's see. Where am I here? Absent nuclei. So it's just doing a balance to figure out what the size of the bubbles are. And showing that like at the temperature of vaporization is high, you get these tiny bubbles. So 0.1 microns, 100 nanometer bubbles forming. And these are like nuclear reactors approaching these temperatures when you get near the core of the reactor. Right. So having those bubbles in there leads to that kind of metal degradation that was so anyway, so what is this thing? This is another form of the Gibbs-Thompson equation. So this is for if you're crystallizing from solution. And again, like, so if you have an equilibrium balance between like salt and water, if you want to crystallize salt, you like put in a lot more than the equilibrium concentration. So you supersaturate the solution. And like in this calcium carbonate, and we're supersaturating to much higher than actually they supersaturate up to the crystal composition, which is pure calcium carbonate. So they go to 100% solute, at least in their simulation. But so anyway, so if you want to get small particles, then you go to high supersaturation. It'll be like log of the supersaturation gives the smallest particles. You need to get really far from equilibrium to get good small particles. This is used or was used like in the 1980s and 90s to make photographic film, like where you had to have high resolution silver nitrate particles. So they would make it from solutions. So there were books written basically on this subject. You'll find books written basically on this form of the Gibbs-Thompson equation to make nanoparticle silver nitrate particles to get less grainy photographs. Once digital photographs came along, this was kind of went out the window, except for artists, who want to have, there's still artistic use of photographic film, but other than that, I think it isn't used. Recording media and things like that, maybe this is important, like for magnetic recording and things. So anyway, there's still people interested in small particles, just not for the same use. But all the theory that came out of this and books that were written were all about, they were all funded by like Kodak in the 1970s, 80s, and there were huge research groups kind of just doing that work using this Gibbs-Thompson thing. So anyway, Laplace equation derivative, same thing. And then this is the, let's see, chemical potential. So this is Gibbs free energy without the entropy term, VDP. And then the change in the Gibbs free energy is, this is just the Laplace equation. And then from the definition of activity, log of A. So you just say log of A equals gamma, and then you have basically the Gibbs-Thompson from that, I guess. A is, if it's ideal solution, A is X. Then you have log of X ratio. The difference of the logs is a ratio in the argument. So log of this minus log of that is log of this over that. And then that equals this Laplace term. And that's it. That just gives you the Gibbs-Thompson equation, this thing. So it's basically, I think all you need is the Laplace equation, knowing that VDP is the chemical potential in the absent entropy change, and then this log of activity for the chemical potential, and then that just gives you this thing. So it's kind of like a three-step operation to give you that equation. So that's two forms of this Gibbs-Thompson. One's a concentration term, and this other one is like a temperature quench term, T quench term, right, for bubbles. And this is for solution crystallization. So this is like in our paper, in our thing in the calcium carbonate crystallization from solution, except that so this is simple, just goes from one phase to the other. An actual crystallization from solutions, like in protein crystallization, no one really understands how things crystallize from solution. It's kind of a mystery. There's a lot of, so you have to go to supersaturation. And in that case, you're ready to phase separate. So you're in a deep quench. So one option is you do spinodal, because you're in such a deep quench, you could do a spinodal decomposition at the interface and then crystallize. That's one option. And there's groups that are very fond of that option. And then you can go through the higher energy crystal form could form. So you could have polymorph form at the surface, like calcium carbonate. So you could have like 1 of 8 polymorphs form at the surface. And you have like a Gibbs-Thompson transition to form the crystal. That's another option. In the paper, he talks about a hydrated amorphous layer. This is like a more mysterious thing. And somehow that transitions into the crystal. Right, so there isn't like a single, this is assuming there's one step, you go from solution to crystal. But if you have these other things in the middle, well, this simple picture might not exactly fit that, So if you're actually doing crystallization of solution, then you'll see that there's a lot of complications to it. And a lot of it is mystery, like protein crystallization. So you can have like 5 different polymorphs or something like acetaminophen, like Tylenol, right? And only one of those polymorphs is active that you can use in a drug, like to sell Tylenol. So basically, if you have a chemical plant where you're making that stuff, you get one of the wrong polymorphs in it, you can't get rid of it by washing the machinery. Like that, once that polymorph forms, everything will go to that polymorph, and the polymorph is worthless economically. So you just throw it away. So basically, if you get the wrong polymorph in a pharmaceutical plant, then you throw away the plant and build another plant. It's pretty weird. Like, so the pharmaceutical crystallization is pretty interesting. Like that, there's a lot of money that's gone into it, and nobody kind of understands exactly what's really going on in it. Means it's probably a good area for research, but anyway, so good exact. So all right, so this is the whole Gibbs model for crystallization. So this is in that paper. Let's see, I have to do that, then this, then that. So he calls it the oh, I mean, I think everyone calls it this classical something, nucleation theory. So he calls this classical CNT, which could also be carbon nanotube. And actually, everyone calls CNT carbon nanotube, but he calls it classical nucleation theory. So, and then he gives the thing about the rate. So the rate of crystallization is, there's going to be a barrier energy. Barrier energy has to do with the bulk. So you have a volumetrics. This is for a sphere. This is for the surface of the sphere. So you have the bulk free energy, which have enthalpy and entropy, and then this surface energy. And then from that, you can calculate the surface energy from the activities. All right, he gets this GC from that kind of approach, and then he figures out what the rate of crystallization is from that. So he calls that the classic CNT, classic nucleation theory. I think this is just called the Gibbs. Everything here is Gibbs, so calling it Gibbs isn't really identifying it, but we just call this the Gibbs crystallization nucleation theory, whatever. All right, so Gibbs-Thompson is that business about growing nanoparticles. Gibbs nucleation theory is this business that you have a volume, and then you have a surface, and the two terms, and then you have the equilibrium. Equilibrium Gibbs transition from liquid to solid. Take the derivative, set it equal to 0. This is r cubed, that's r squared. You divide by r squared, you get r. So you get some magic r from that. It's going to be something like the surface tension over the bulk and energy of fusion, which would be like delta H usually. So you have 2 times the surface energy divided by delta H is this r star. The surface, if you have higher surface energy, you get larger particles. Higher fusion, you get smaller particles. And then you take that r star at some temperature. This depends on temperature, this doesn't. And then you plug that r star back into this equation for delta G, and you can get the delta G for that r star, which would be the maximum delta G in the curve. And then you can get the barrier energy, which he uses to figure out the rate of crystallization. We'll plot of that in here somewhere. Let's see, this is slide. That's slide 30. Here. So as you go across particle size, you reach r star, and then that's the barrier energy to crystallize. That delta G will increase till you reach r star and then like drop down. So derivative dg set to 0, that's this peak value. So when you go to larger particles of bulk, the surface, let's see, the surface kills you. Let's see, delta G drops due to surface at the high end. So the surface is negative, so it drops the delta G here. Delta G drops here because of the bulk. And there's a happy medium where you have R star, which is a magic thing to grow. And this is showing that how R star changes with temperature, because delta G, the delta H of this expression, delta G changes with temperature, so that the R star changes with the temperature that you crystallize. So again, if you want small crystals, you go far from equilibrium. So you go to the deepest quench that you can get. One would be the equilibrium melting point. You make infinite crystals. If you want to make small crystals, you quench it to a deep temperature, to a low temperature, supersaturate, and then you can get the small crystals from it. Or you get to the highest concentration above the equilibrium, then you get the smallest crystals. Or temperature, concentration, I think those are the two things you have. And pressure, you can go to super high pressure. So you have like three tools you could use. So this is kind of three forms of the Gibbs-Thompson: temperature, concentration, pressure. And all of them are going to be that the further you are from equilibrium, kind of the more violent the situation, the smaller the particles come out. Right. So anyway, so that's that's good. That's partly in that paper. It's one of the things he talks about. Or they talk about, but we got that. This is what's called classical nucleation theory. Then you get to this issue. So this is all what's called homogeneous nucleation. So you have just your liquid floating around, then you're going to make crystals on it, right? Like almost like, but we know that doesn't happen. Like if you're in the nucleation and growth region, you need to have dirt. The crystals form on dirt. They don't form spontaneously. Only if you're in the spinodal region do they form spontaneously, so deep quench. So anyway, so the normal situation would be you nucleate on dirt that's in the system, and then the phases grow from that. The reason for that is that the heterogeneous nucleation takes half the energy. Like, or the size of the phase is going to be half the size for heterogeneous nucleation. And for heterogeneous, the energy is basically going to be half the energy too. So that barrier energy, the barrier that you see here, for homogeneous is going to be here. If you go to heterogeneous, it'll be half as big. So if that's 1, this will be 0.5. So if you have dirt, you'll crystallize on the dirt first because it takes less energy to do it. Like you'll have energy to crystallize there. So how that works with this Gibbs approach. Instead of having a cubic term, you have a square term. And then you're going to crystallize like a circular plate onto a surface, right? So it's got pi r squared area times the thickness of the plate that you're crystallizing. And then the growth front of it. So the energy, so if you grow that thing, it's going to only grow laterally, not volumetrically. And it's going to just cover up the perimeter, right? It's just the growth of it would start from a spot and then would grow out. So it's just the perimeter, which is 2 pi r times the thickness of the thing that you're growing. So the perimeter is a growth thing times gamma gives you this heterogeneous crystallization. You set that to 0. Also, you have squared and single, so you end up with a size out of it, and you get this magic size. And it turns out that magic size is half of what you had for the homogeneous. You can make smaller crystals, but they're stuck to a surface. It's kind of like a catch-22. You can't collect these crystals because they're stuck to a surface, but they're half as big as the ones from homogeneous. I mean, if you're making surface structures, that could, like if you're making electronics, that could be a good thing because you want it stuck to the surface anyway. But anyway, so then you take that number, plug it back into your equation for the heterogeneous, and you end up with this equation. It turns out that that's a smaller number, like about half what the homogeneous nucleation energy is. I mean, like 1/8 of the, so kind of smaller, whatever, like 9/80ths of the homogeneous. So that means that if you have the opportunity to do heterogeneous, you'll do it. Like that'll happen immediately because and then what will happen is that will deplete your, say you have a supersaturated solution, but once you start nucleating, the saturation drops, like you're sucking the material out of the solution, so you don't have a supersaturated solution anymore. So these dust particles will eat up everything that's there, and there won't be anything left for homogeneous. So it isn't like there's a competition between the two. Like the one will just take all the stuff away, take everything, and it'll just be surface nucleation. So anyway, this paper is on competition between those two. You don't hear much about the heterogeneous nucleation model. Usually people just talk about this, like in this paper. So you might notice that, like in this paper, this calcium carbonate paper, whatever that is, this Freeman thing. So I mean, obviously this is heterogeneous crystallization, right? Like he shows a picture, he's crystallizing from this, whatever it is, CNT, what is it, classical nucleation theory, onto a surface. I mean, without the surface, he's got a model where he builds a crystal first, puts in this amorphous hydrated solution on the top that's super saturated, and then watches it crystallize. So I mean, why does he start out with this equation? You know, this isn't, it should be R squared and then R, like the heterogeneous equation, not the homogeneous. Just saying, you know, so it's kind of funny that it's kind of funny how he does it. Well, he's got a nice discussion in the first paragraph about kind of the nuances of crystallization from solution, polymorphs and whatever, and he has some references to it. But basically, there's kind of a flaw that he gets to this point, and he starts talking about homogeneous nucleation. And then when he does the simulation, it's obviously heterogeneous nucleation. So the rules don't apply to that. They aren't exactly the same. So anyway, it's just kind of an interesting nuance. I don't think it impacts much what he's talking about. Anyway, so what do we got? We're almost out of time here. So I managed to waste an hour or two. So yeah, so there's a lot more in this chapter to go through. These are main points, though. Hopefully, you can kind of retain some of this. The Oswald ripening also has to do with this business, like swapping out the pressure for the chemical potential and talking about the phase growth. So you can write the Oswald equation for Oswald ripening based on that same trick about calling the pressure dPdV is or VdP is the chemical potential, and then like G is VdP, and then so you can swap out dP for chemical potential, divide by V, and then end up with this. Or you can multiply V here to get chemical potential, you have to multiply there, and then once you do that, then you can get this expression, right? So anyway, it's possible. So that's the same thing as this, like the V gamma 1 over R, and then the two phases in competition. So the two solid phases, two different polymorphs, or a large and a small crystal of the same type. So this can be used for both two different polymorphs with different chemical potentials, or also two different sizes, because the different sizes will have different R's. So the Oswald ripening can be the same crystal, just different sizes, and the large ones will be stabler than the small ones. They'll have a lower chemical potential, meaning they're stabler. And there's lower G. So, or it could be two different polymorphs, so the same crystal, less stable and more stable. So anyway, so all these things are kind of like fall into the same thing, like kind of Laplace Gibbs-Thompson equation type thing. Anyway, yeah, so why don't I quit there, and then next time I'll pick up here like slide 38 or something, and then go through that paper again. Yeah. This thing. Yeah. Do you have any comments?